Hello, everybody. My name is Uzay Emir from School of Health Science, Purdue University. Today, I'm going to talk about our novel Rosette Petal trajectory for phosphorus spectroscopic imaging. Our title will be Fast Three-Dimensional Phosphorus Spectroscopic Imaging using custom Rosette Petal trajectory at 3 Tesla with up to 4 times acceleration using compressed sensing. I have no financial interest or relationship to disclose. As all we know, spectroscopy is able to profile chemical composition of defined region of interest. Since our body full with hydrogen atoms, it is most commonly used technology for spectroscopic approaches. Phosphorus spectroscopy is the oldest spectroscopy methodology, does not suffer from the problems of hydrogen such as water and fat contamination, and requires less homogeneous magnetic field. And once we have optimal acquisition trajectory, it provides useful information such as phosphocreatine, ATPs, and phosphocholine that are related to the phospholipid metabolism. However, although it is oldest, but it is not the attractive one because a lack of technical development and integration into the clinical MRI system is the biggest barrier against the phosphorus spectroscopic imaging, most likely originating from low signal to noise ratio, poor spatial resolution, long acquisition time, and lack of processing software available for automated quantification of the metabolites. So, in this talk, what we are trying to achieve is make the phosphorus spectroscopy as attractive as it was before by providing improved signal to noise ratio, improved resolution, reducing the acquisition duration, and make the quantification automated and minimize the user interaction starting from acquisition till processing. In order to achieve that, we pick our novel acquisition strategy, which is ultra short echo time phosphorus 3D spectroscopic imaging at 3 Tesla with novel K-space trajectory. As we recently showed that this K-space trajectory is superior compared to the radial partners, not only for signal to noise ratio, but also the keeping the resolution as similar or even better compared to the radial partners. All those benefits could be quite useful in the case of phosphorus spectroscopic imaging where resolution is and also signal to noise ratio is the problematic situation. So in order to achieve that, we try to use the surface coil for the 5 subjects, and we use Siemens Prisma 3T scanner, and ultra short echo times parameters are listed as on the table. Most importantly, our spectral bandwidth without doing any spatial and temporal interludes is 2.2 kilohertz. Our acquisition delay from the end of the RF pulse is 10 microsecond. It is most likely the shortest delay that is achieved for spectroscopic imaging, and number of averages is 3. Total acquisition is about 27 minutes. For the post-processing, we chose non-uniform Fourier transform in addition to the compressed sensing. And also, we use LC model for metabolite quantification. We repeat these procedures for different acceleration factors up to 4 times. As illustrated in this figure, we have the metabolite maps of ATP to phosphocreatine ratio. From bottom to top, the acceleration factors ranging from 1 to 4. As bottom, we have the acceleration factor 1, and at the top, we have the acceleration factor 4. As you can see, this overall representation of the metabolite distributions are quite similar. However, acceleration factor of 4 has severe inhomogeneities in terms of the detectability of the metabolites compared to the acceleration factor 1. As we look at the single spectra from the occipital cortex, you can see the degradation of the signal to noise ratio, but overall representation of the metabolites are quite strikingly the same between different acceleration factors. So as we look at from left to right, acceleration factor ranges from 1 to 4, and that corresponds to acquisition duration from 27 minutes to 6 minutes and that makes the acceleration fast enough for clinical purposes. And the SNR degradation is not as striking as the decrease in acquisition duration. So, conclusion. In this study, we demonstrate that our novel Rosette K-space trajectory not only provides the signal-to-noise ratio increase, but also increase resolution, and also reduce the acquisition duration, and make the quantification of the metabolites automated and minimize the user interaction. So these technical advances make phosphorus spectroscopy a viable option clinically, and it is now appropriate to develop and evaluate the protocol suitably for clinical practice and use them investigated brain metabolism. Thank you so much for your listening, and these are the collaborators who contributed to this work.